My net is slow right now, so
Okay,
sorry,
so
Vihar.
oh sorry, that is your father's name. Sorry.
Yes.
Yes, so Bihar. Okay, I'll just give a quick recap of what I answered, Somi. So in a project, all of you are assigned a particular topic. You're supposed to study that particular topic from a group theory and linear algebra perspective. So for example, if you are given a particular group as a topic, you are supposed to find out everything, its properties, those properties that we have studied. So for example, order of the group, is it abelian, what are its subgroups, etc., etc. Okay. There could be some properties that we may not have studied, but that is something that you can dig out from the literature. And in case your group happens to be a group which has applications, you can look and study a particular application or two. And then towards the end of the semester, you're supposed to write a LaTeX report, submit it, and then give a presentation as a group. And in the presentation, I may ask randomly anybody to give a presentation. So don't delegate the task of presenting to a specific member of the group.
Okay, sir. Got it. Thank you, sir.
Right. Okay. So let's go ahead. Linear algebra. So we were looking at this specific question. Ax equals b. We were trying to solve for x. A was an m by n matrix, okay, containing only real numbers for now. B, the right hand side vector, be m by 1 matrix or a vector, and you need to find an x which is in Rn. Okay, and we came to the conclusion that solution to x equal to b exists if and only if b belongs to the set of all possible linear combinations of columns of B. Is that clear to everyone? Okay, I'm assuming it is. So this sort of the set of all possible linear combinations of columns of A is a very important set, because the solution to a linear system exists or not, it depends on this set, right? Even if I change the right hand side vector B, then if I pick some element from this set, the solution will exist, otherwise no. So this set deserves a special name. Okay, and the set of all possible linear combinations of columns of A is called the column space of the matrix A. Why is it called space? It will be clear soon. For now, just assume that this is the name given. And why do we need this special name? Because, as is obvious from the first point, whether a solution exists or not, depends solely on this set. Okay, and the notation is C of A. Okay, mathematically, the set consists of all AXs for all possible values of X in Rn. Is that clear why the column space can be defined in this way? See, all linear combinations. How do I get linear combinations, right? By choosing different values in the vector X. Matrix A is fixed, but the way in which we can perform linear combination, basically the scalars, right, or those real numbers which get multiplied to each column, those can be changed. since we want all possible linear combinations, so this real numbers x1 to xn should be allowed to take all possible values. Is that clear?
Yes, sir.
And so x can take on any value in Rn. This set, the column space, will be of course a subset of Rn. Okay. Now let's try to sort of justify the term space. Okay. Why not column set? Why column space? It has certain properties. So let's pick the zero vector in Rn. Okay, so this will be the notation. If I want to write a vector whose entries are only zeros, and if there are m such entries, I use this notation. Bold 0, subscript m. First question, does this vector belong to the column space of any given matrix? It's a very simple question.
Yes, sir.
How?
So because for every means for for x set we will be having a zero, at least a
Right.
zero. So
Yes. So for x equal to 0n, we'll see that no matter what your matrix is, right? It can be any matrix of size m cross n. In that case, a multiplied to 0n will always give you 0n. Okay, so obviously the answer is yes. Second question. If I pick two elements from this column space, okay, and I arbitrarily choose real numbers, and I perform a linear combination of these two vectors in this way, what can you say about this element?
So it will
It
also
will
belong
also
to
lie.
our space
Why?
because we are taking a linear combination of elements inside it.
Still, can you prove it? So if B1 belongs to CA, what can we say? What does it mean?
B1 equal to AX1.
Right. So there is some x1 in Rn such that AX1 is B1. Similarly, AX2, there will be some x2 in Rn such that AX2 is P2. Okay, then what is PB1 plus QB2? It's nothing but A applied to Px1 plus Qx2. Okay, so therefore, this belongs to column space only. Here, so these two properties sort of justify the term space. What do you mean by space intuitively or in a common sense world? Space like it sort of extends infinitely, right? In all directions. Or at least if there is some direction in which there is so-called space, then it can go on in that direction infinitely long. So its properties too especially encapsulates this intuition that we can column set can be extended infinitely. Okay, so this P and Q can be arbitrary large, they can be real number, sorry, they can be negative numbers as well. So in both directions, if B is in column space of A, 2B is also in the column space of A, 10 million times B is also in the column space of A. Similarly, minus 10 million times B is also in the column space of A. Okay, so that is the reason why this space makes sense. Technically, this space has a very special definition that we'll see later on in the course, but it's basically the second property. Okay, right. So, so as of now, we have looked at this problem, right? That given Ax equal to B, we were worried about whether the solutions exist or not. Now, let us talk about multiple solutions. Okay, so if Ax equal to B is the linear system of equations we are trying to solve, let us say there are two solutions. Multiple means at least two. So x and y are two solutions of this system of equation, which basically means Ax equal to B and Ay equal to B. And since these two are different solutions, x is not equal to y. What can we say about this? What will happen? So if we subtract these two equations, what will we get?
A into x minus y is 0 vector.
X minus y is equal to 0 vector.
Similarly, right, if there is a vector z, right, which let us assume is not 0, but not written over here, but assume z is not the 0 vector. Okay, then Az of course is the 0 m vector. If Ax is equal to B, what can we say about A of x plus z?
This will also be B.
B, right? So, therefore, since z is not the 0 vector, x and x plus z are two distinct solutions. It basically means multiple solutions. So, what can we conclude from these 2 points? So if there are multiple solutions, then what can we say about the vector x minus y? Will it be 0? X is not equal to y, right? So x minus y, of course, will not be 0. If I call this x minus y as z, denoted by z, z is a non-zero vector such that Az is equal to the 0 vector. Agreed? And in the last point over here, what did we derive? If there is a non-zero vector z such that Ez is the 0 vector, then I have multiple solutions. So this is equivalent, right? Does that make sense?
Yes.
So that is why this set of vectors, right, such that Ax is equal to the 0 vector is very important. Okay? That set tells us whether for a particular system there would be multiple solutions or not. And that set is what is called the null space. Okay, so given any matrix A of size n cross n, okay, the set of vectors in Rn that get mapped to the zero vector is called the null space. Okay, and it is denoted by n of A. Mathematically, it is basically set of all vectors x in Rn such that Ax is the zero vector. And of course, this is a subset in Rk. You probably are familiar with this concept. You've come across this earlier, isn't it? Not in terms of matrices, but in calculus. Do you remember something like this? Does this ring a bell?
Central group.
No, I'm saying calculus.
Okay, sorry.
There also there is, I mean, it has of course relation to group theory. That also we'll look at it in the same slide. But before we get there, you remember that you have encountered this in calculus. Not in terms of matrices. Okay, maybe I'll give you a clue. Okay, when the right hand side vector is 0, right, that linear system is called a homogeneous system of equations. Does that ring a bell?
Yes, sir.
You must have solved homogeneous linear differential equations. Yes?
Yes, sir.
Okay, so this is the same thing. It's just that instead of a differential equation, remember it's not just any differential equation, it is linear differential equations. Okay, and here also we are just looking at linear systems of equations. So there has to be the same structure at both places. And what do you call solutions to Ax equal to B? In the language of linear differential equations? You recollect?
Solution.
What solution?
Non-homogeneous equations.
Okay. I think at least I used to call it particular solutions. I don't know if you have come across this term or not. Anyways. Okay, so this is going, I mean, this is basically the same thing. See, a linear, it's a second order differential equation, d square y dt square plus 5 dy by dt plus 10y equals 0. I can write this as a matrix. Square by d square by d 5 plus y 0. Okay, so this is like a y 0. Since you're not doing anything different over here. Okay, let me sort of show the analogy with groups. So this matrix A, right, it operates on what vectors? So what vectors can be multiplied to this matrix on the right? In other words, x comes from Rn, right? And what do we know about Ax? Which set will Ax belong to?
Rn.
Rn. Now Rn with the component-wise addition, what does it form? And similarly, Rm with component-wise addition, what does this form? A set with one binary operation. Okay. What do we know about that set? Does it have the identity for that particular binary operation?
Yes, sir.
Yes, it's the zero vector, right? Then how about inverse?
Yes.
Yes. Associative?
Yes.
Yes.
Yes. Okay. Closure?
Yes.
Yes. So what do we have?
It is a group.
Yes, sir.
They both are.
Both are groups. And what kind of groups?
Abelian groups.
Abelian groups. And what is this function? A mapping this group to this group. What kind of a function is it? So Ax plus y is equal to Ax plus Ay. Is that right? This is addition plus n. This is addition plus n. Is that right?
Yes.
Yes. So what is this map?
Homomorphism.
Homomorphism. Good. And in fact, it does not matter what your matrix A is, right? Any matrix, this first equation is true. So therefore, A looked upon as a map between these two abelian group is a homomorphism. So then what is null space of A?
Kernel of.
Exactly. It's kernel of. Okay, so in sort of more standard math books, will encounter this notation for null space, ker of A or kernel of A. Okay, so don't get surprised. That is because in such cases you are looking at this homomorphism. Okay, so yes. Okay. That is the analogy with our group theory. Okay, let's look at the properties of this set also, or in other words, let's try to justify the term space. Okay, how about this vector 0n? Will it belong to the null space of this matrix A, of any matrix A? That's
Yes.
right. It's trivial. I think we just wrote that down on the slide of column space. 0n, since any matrix of size m cross n will map 0n to 0m, so 0n will always be an element of the null space. How about linear combination of elements in the null space?
Yes, sir. This
This will also belong to the null space. Okay, so again, this particular second property sort of justifies the term or the phrase space associated with this particular set. You can extend in any direction if that direction is in that set. That is basically what it means. third property we have already seen. If there exists a non-zero vector z in the null space of A, then what can we say about the solutions to Ax equal to B?
Multiple solution.
Sure?
Yes, sir.
But I have not given you anything, any information about B. So will for any B a solution, does the solution exist? The question.
Non-zero B?
For any non-zero B, are you sure that solution will exist? So for example, what happens if the matrix A contains only zeros?
Then B should also be 0.
Yeah, but that's what I'm saying, right? I'm not saying anything about B. Can we make such a general statement that if there is a non-zero vector Z in the null space, then Ax equal to B will always have multiple solutions?
If A is a non-zero vector,
Vector, why should A be
it
non-zero?
is non-zero.
Acha, for any non-zero matrix A,
And a non-zero B.
B. Why non-zero B? What is the problem if B is 0?
Yeah, B can be anything.
B can be anything. So if B is anything, you still guarantee that there will be multiple solutions.
Given that A is
Non-zero.
non-zero.
Okay, think about it maybe for 20 seconds. Something missing in your statement.
Sir, given that AX equals B have at least one solution,
Right.
and
Exactly.
for Z, Z belongs to N of A, we can guarantee that we have multiple solutions.
Right. Because if I don't specify that B is in the column space of A, right? The null space can be anything, doesn't really matter, but there will be no solutions, right? So Ax equal to B will have infinitely many solutions if one exists. Okay, that's important because B, as we just discussed in the beginning of the class, if B is not in the column space of A, full stop, right? No solutions. So if there is one solution to X equal to B, then if there is a non-zero vector in the null space, we guarantee that there will be infinitely many solutions. Not 2, not 10, but infinitely many, right? Why?
Linear combination.
Exactly. So for any vectors z in the null space, you can make a new solution, x plus z. If z is in the null space, so is 10 times z. So is square root 2z, right? So you can create, if there is a one non-zero vector in the null space, there are infinitely many vectors in the null space, and therefore there are infinitely many solutions if one solution exists. Is that clear? Anybody who has issues with this?
Sir, can you explain it again?
Which part?
This last part only.
Okay. So what I'm saying, so we have studied two situations, right? One is we are asking the question, when does the solution to Ax equal to B exist? And now we are looking at the part, looking at the question where when does multiple solutions exist?
Hmm.
Okay. So what I'm trying to say here is in this first part of the slide, we saw that if there are multiple solutions, then there will be a non-zero vector z such that Az is 0.
Hmm.
Okay, and vice versa, if there is a non-zero vector z and if Ax is equal to B, right? So don't, this is important, right? This part. If Ax is equal to B, then so is A into x plus z. That also is equal to B.
Hmm.
So these multiple solutions is directly tied to whether there is a non-zero vector z such that Az is equal to 0. So all vectors z such that Az equal to 0 are very important, right? Because it allows us to answer this question whether there will be multiple solutions or not. Which is why that set also deserves a name. The name given is null space. Null is like 0. Right? So, and we saw that if there is one non-zero vector in the null space, right, then you can have infinitely many non-zero vectors in the null space because of this second property.
Hmm. Yes.
Right? If x is in the null space, 10x will also be in the null space, 100x will also be in the null space, and all of these are distinct elements.
Hmm.
So there will be infinitely many elements in the null space if there is one non-zero element in the null space. For
Yes.
every distinct element of the null space, you can construct a new solution. Right? If x
Hmm.
is a solution, x plus z is also a solution. X plus 10z will also be a solution. X plus 100z will also be a solution.
Hmm.
So if there is a non-zero vector z in the null space, okay, and if there is a solution to Ax equal to B, then this guarantees that there will be infinitely many solutions. There is no midway. So either there is no solution, or there is one solution, or there are infinitely many solutions. You will never have a system which has only, let's say, 10 solutions.
Okay, because that null space have infinite solutions. That's why.
No, the null space has either, see, for sure, from the first property, null space of any matrix cannot be empty.
Hmm. Yes.
Okay, so it will have at least one element. If it has only one element, then
Then only one solution will exist.
if it exists, that is important.
Hmm.
Okay, you may have only the zero vector in the null space, but still there may be no solution for some Ax equals B. Can somebody give me an example?
So for zero vector,
So a system Ax equals B such that the null space of A has only the zero vector. But Ax equal to B does not have any solution.
so sir, when B is non-zero vector,
Then what happens? But give me the matrix A.
eh,
Sir, we can take example of parallel lines.
Yes, but can you now give me the matrices? But will it have a parallel lines means what? Is that going to guarantee this?
Sir, the parallel lines, they have no solution, but their null
No,
space
but
have one
exactly.
element.
One element is, I mean, one element is guaranteed, more than one element. See, for example, 2, 3 and 2, 3 x, y equals 5, comma 6. This is parallel lines, right? Does everybody see that? That these are parallel lines?
Yes.
Right? But if I look at this matrix A, will the null space have only the zero vector?
So the null space will have the all the points on the line.
All points on the line. Which line? Why would it have points on the line?
I'm so sorry, sir. Sorry, sir.
So I can see clearly this is one vector in the null space. Yes or no?
Yes, sir. Because multiplication gives 0.
Right. Okay. But I'm looking for this situation where the null space has only the zero vector and still Ax equal to b does not have any solution. Is that possible? Take that as a homework.
So it is not possible in 2 cross 2. We have to
Fine.
get.
So see, I never said that A has to be 2 cross 2. It's just somebody said, gave me this example of two parallel lines, which implies A has to be 2 by 2. But for any M and N, construct such an example.
Sir,
Yes?
sir, I have one doubt. Is it necessary for A to be a square matrix?
No, no, no. Nowhere have we assumed that, right? A is it started out with Rn, Rn. So we have never assumed that A is square. What to write it? I think it should be obvious because I chose this
Yes, sir,
Rn
but
and Rn.
in all the examples that we took, A has always been a square, so that is why I was asking.
That's fine, but that is what I said in the last class, that we are generalizing. I know all of you have solved only 2 by 2 matrices and 3 by 3. Now, one small generalization is you need to work also with a rectangular system of equations. So yeah, do not assume that A is square, which is why I'm keeping it general, M and N. Yes, so can someone give me this example?
Yes, sir.
Okay, go ahead. For sure, there exist, I mean, thousands of examples of this kind.
So 1,
What is the size of the matrix?
3 cross 3.
3 cross 3. Okay, interesting. I don't think it's possible. Let's see. Follow. First column.
Column, sir, column 1, 1, 2, 2, 2, 1, and 3, 3, 2. And B vector is like 5, 6, 4.
So why do you think the null space contains only the zero vector? The null space. No, the null space will have infinitely many elements for this matrix. Okay, so no, this is not the right example. Let me not waste more time. Give you a very, very, very simple example. So let A be this matrix 1, 0. Okay, and X is just one X. Let's be 0. This is my A. X is in R. This is my B. A is R. Then to R. I hope you see why this is in the why the null space is only 0. Is the null space? What is the null space?
0.
0.
And will there be a solution?
No.
No solution.
Okay, I hope I've answered your question. Yeah, I've
Yes, sir.
deviated a bit too much. I don't know.
Mm-hmm.
Okay, so please remember you may have a situation where the null space contains only 0. That does not guarantee that you will have unique solutions, right? It may be possible that there may be no solution at all. Okay, so all we are saying is if the null space contains non-zero vectors and if a linear system has at least one solution, then there will be infinitely many solutions. Okay, it may so happen that the null space has infinitely many elements, still Ax equal to B may have no solutions. That is also possible. I mean, from this example, can you construct such an example? Very easy. Maybe take that as a homework.
Sorry, sir, can you repeat?
So we have seen this example where the null space has only the 0 element or the 0 vector, and still Ax equal to B has no solution. Forget uniqueness. Okay, it has no solutions. Similarly, can you construct an example of a matrix whose null space has infinitely many elements, but still Ax equal to B has no solutions?
Sure. The above example is
Above example, right? Exactly. Good. Example 2, it has, saw this equation. This vector belongs to the null space, and therefore there are all multiples of this also belong to the null space. So there are infinitely many elements in the null space. If you try to solve this system of equations, you will find that there are no solutions. Okay, so all these possibilities exist. Just be careful. Don't assume something. Now let's try to dig into this multiple solution case. Okay, so there is some non-zero vector in the null space of A. What can we say about the columns of this matrix A if the null space has a non-zero vector? That is what we're going to study next. Okay, so if there are multiple solutions to Ax equal to B, that means there exists a non-zero vector Z in the null space of matrix A, right? Now, if I expand Ax or Az, sorry, not Ax, okay, because we saw that when we multiply a vector to the right of some matrix A, all we are doing is we are taking linear combinations of columns of A. Is that fine?
Yes.
So this is just Az. And again, this is the notation for ith column. Okay, the column index is fixed. This will give me 0, and since I'm assuming that Z is not the 0 vector, at least one of these Zi's will be non-zero. Okay, so let's assume that the kth entry of the vector Z is non-zero. There may be more than that which are non-zero, but at least Zk is non-zero, right? I hope that is clear. So in that case, what I can do is I can take Zk A star k on the right hand side. Right? I can rewrite this as Zk A star k equals minus Zk A star k equals summation I going from 1 to n, I not equal to k, Zi A star k. Right? And I can divide both sides by minus Zk. Sorry, this should be A star I, not A. Okay, is this making sense? I hope you realize why I needed this assumption that Zk is not 0, because I'm going to divide Zk both sides. Is that fine? There is a small typo. I'm just rewritten this. This should be minus. Forgot that minus sign. So the interpretation of this equation is that using linear combination of all columns except the kth column, I can construct the kth column of the matrix A. There is someone whose microphone is not muted. Can you please mute yourselves? Oh, thank background noise coming in from somewhere. Please mute yourselves. Bihar. Right? So the interpretation of this particular equation is the kth column matrix of the matrix A can be constructed by a certain linear combination of the remaining column vectors of the matrix A. Is that right? It'd be good to get some feedback. Are you all following this?
Yes, sir.
Yes.
So then we say that these set of column vectors, right, all n of them, including the kth one, right, we say that this set of vectors is a linearly dependent set of vectors. Okay, the definition of linear dependent set of vectors is that even if one column or one column vector from this set can be written as a linear combination of the remaining set of vectors, then that entire set of vectors is linearly dependent. Okay, please remember, even if one of the vectors can be written as a linear combination of the remaining vectors, may be possible that there is some vector that cannot be written as a linear combination of some of the other remaining vectors. Okay, but the definition is even if one vector can be written as a linear combination of the remaining set of vectors, then that set of vectors is said to be linearly dependent. Okay, and the complementary concept is that of linear independence, okay, or linearly independent set of vectors. It simply says that if that set of vectors is not linearly dependent, then we have a linearly independent set of vectors, which means that none of the vectors can be written as a linear combination of the remaining vectors. So this is a very, very, very important and crucial concept in linear algebra. Basically, like if you understand this, then nothing is difficult for you. Everything depends on this concept. I'll repeat the definition once more. A set of vectors A star I going from 1 to n, is said to be linearly independent if that set of vectors is not linearly dependent. Basically means if none of these vectors A star I can be written as a linear combination of the remaining vectors. Okay, so for example, what I mean by remaining is if I want to get A star k, I cannot use A star k on the right hand side. That of course would be trivial, right? A star k is 1 times A star k. Okay, I cannot use the kth vector in order to obtain the kth vector itself, which is why the emphasis on the remaining vectors. Is that clear?
Yes, sir.
Okay. So now another way to define linearly independent set of vectors is, so let's say there is this linear dependent set of vectors, A star I going from 1 to n is linearly dependent, which means that there is some A star k such that it can be written as a linear combination of the remaining vectors. Okay, so Zi A star I. Now I can take everything on the left hand side to get A star A plus I going from 1 to n I in short I star I going from 1 to n is equal to the 0 vector, right? And where zk is just -1, right? So it is, if I have a linearly dependent set of vectors, it is possible to get a non-zero linear combination of these vectors such that the linear combination is equal to the 0 vector, right? As far as I have a linearly dependent set of vectors, using some non-zero scalars, it is possible to construct 0 as the linear combination of these vectors. That is how I will interpret this equation. So what can we say about a scenario where your vectors are linearly independent? Can I construct a linear combination of these linearly independent vectors and obtain a 0 vector?
No, sir.
No? Sure?
Yes, sir.
No, I disagree. There will be a certain linear combination even if your vectors are linearly independent, so that I will get the 0 vector.
For coefficient 0.
Exactly. Right? If all these zi's are 0, it doesn't matter what the column vectors or the what vectors you are considering, I will always get 0. So that's basically saying that if I pick z to be the 0 vector for any matrix A into 0 is 0. Okay, but if I have a linearly independent set of vectors, then that is the only possible linear combination in order to get the 0 vector. That is yet another equivalent definition of linear independence. Okay, a set of vectors A star I going from 1 to n, is said to be linearly independent if if you can construct a linear combination of 0, but the only way to do that is by using only 0 coefficients or 0 real number. Okay. Right. So this is an equivalent definition of linear independence. The only way to construct 0 using linear combinations of these vectors has to be by using 0 as the multiplication. Okay, if that is something you can prove, then that set of vectors will be linearly independent. Then let us now define the column rank of a matrix. Okay, so if I'm given an m by n matrix, okay, the column rank of the matrix is nothing but the number of linearly independent columns of that matrix. Okay, I hope the definition is clear.
Yes, sir.
Sir, I am having a doubt.
Go ahead, Tarak.
Sir, here for us, the a vector is also a column matrix, right, sir?
Once again.
Sir, means a vector is a column matrix, right, sir?
Yes, yes. I'm always assuming any vector is written as a column matrix.
Okay, sir. Sir, then given a matrix, what can we say about the number of linearly independent columns?
That is what is called the column rank. Can you be more specific?
Means,
So,
is there uh, yes, sir.
go
Means,
ahead.
is there a condition that column rank is not means column is there any constraints on column rank of a matrix?
Yes, there are, and we are going to look at it shortly.
Okay, sir. Means it is always it will always be it will always be less than the number of columns of the matrix, right, sir?
Of course, that is, I hope that is clear to everyone.
That
I
is clear.
cannot have more number of linearly independent columns than the number of columns, right?
Yes, sir. Means I was asking if there are additional constraints than that.
There are additional constraints.
Okay, sir.
The column rank of a matrix has to be less than the minimum between the number of rows and number of columns. Cannot also be greater than the number of rows in the matrix. Okay. So if I have a 2 by 3 matrix, for example, the column rank has to be less than equal to 2. And we'll see why anyways. So let's proceed with this. Now, once we have introduced the column rank of a matrix, the obvious question is there must be something like a row rank also, right? There is column rank, then there should be row rank as well. Before we get to that, let us introduce this concept that I'm sure all of you are familiar with. That will help us deal with this column and rows in the same manner. Okay, so transpose of a matrix, I hope all of you have heard of that. Yes or
Yes,
no?
sir.
Yes.
Yes. Okay. Right. So basically, transpose of a matrix is you exchange rows and columns. Okay, so if you have an m by n matrix, the transpose of that matrix is an n by m matrix. Okay, where the first column is the same as the first row of the original matrix, and so on and so forth. The second column is the second row of the matrix, and so on and so forth. The transpose of the matrix A will be denoted by, and this is one of the popular notations. There are several other notations. Okay, so depending on what kind of book you are reading, there may be slight differences in the notations. Also be careful with my notations here. So as you can see, this is nothing but the first row of the original matrix A written as a column matrix. Okay, so that the notation is A1 star, simply because the first index remains fixed. Okay, so this refers to 1 star. A1 star refers to the first row of matrix A, but this is written as a column matrix. Okay, so first row of matrix A written as a column matrix. Okay, this is what this notation will stand for. You can written it here also. Be careful with this. AI star denotes the ith row of the original matrix A. Okay, but written as a column matrix. If I want to write it as a row matrix, what should be the notation now? Anyone?
It should be AI star transpose.
Transpose, exactly. This will be ith row written as a row. Okay, I didn't want to sort of write A1 star as a row matrix because then it will confuse you. Okay, so unless there is a transpose, at least in this course for my notations, unless there is a transpose, will be assumed that you are writing the matrix or that vector as a column matrix. Okay, I hope my assumption behind choosing that notation is that it's going to reduce confusion. I hope that is valid. Let's see. Okay, so I think we'll stop here for today and we'll look at the column spaces of the transpose of the matrix, the null spaces of the transpose of the matrix, and we'll also see that row rank is nothing but the column rank of A transpose, which has to be the same as the column rank of the matrix. Okay, that is what we discuss in the next class on Friday. Okay, so thank you and hope to see all of you in the next class.